Hello everyone, my name is William Ortola Leonard. I am a PhD student at the University of Florida working with Zach Slepian on the 4-point correlation function to try to prove the universe, but then also to try to prove parity violation. And so let me just start with a small introduction, okay? So as cosmologists, we seek to understand three main things. One is, how does the universe start? How does it come to be? Two is, how does the universe evolve from the start all the way to the present, and then how is it going to evolve from the present towards the future? And third, what are the properties at each epoch of the universe? And so, as it is the topic of this conference, one of the properties that we're interested on understanding in the universe is parity violation, whether the universe actually respects that symmetry or not. And so to answer these questions, we need three things. The first thing is observations. In this case, for us, we need observations about the positions and the three-dimensional position of galaxies. So we need also telescopes that allow us to look and obtain those positions. Then the second thing is math. Some theories that allows us to predict maybe what are those positions of the galaxies, what are the statistical properties of those galaxies, and even more on other observables. And then finally, the third thing that we need is to actually know how to apply both the data and the math, so like the theory, combine them and then extract that cosmological information so that we can answer either of these three questions that we really want to understand. So my work with the 4-point correlation function, which I will be introducing later on, does touch a little bit on most of these three things. So I do want to quickly introduce you to each of these three things and how they relate with my work and or work to support parity violation or the search for parity violation. So let me start with the data. Basically, we live in a golden age for cosmology where we have many different surveys that are operating right now and then that will be operating into the future. And so, for example, for ground-based photometric surveys, we have surveys such as the DES and KITS. Then for spectroscopy surveys, we have the dark energy spectroscopic instrument, DESI for short. And then we also have Foremost. And then we also have space-based experiments such as Euclid. And in the future, we will have the Nancy Grace Roman Space Telescope. Now, specifically, my research uses the dark energy spectroscopic instrument, DESI. Okay, so I just wanted to show you a nice overview of DESI. In this case, for example, in the top left corner, we have a picture of the observatory from the outside, which is located at Kitt Peak National Observatory at Cerro Tululu in Tucson, Arizona. Then on the top right, we have the four main components of DESI. The first one, which is the focal plane, which is where we have this circular plate with 5,000 fiber optics, robotic arms that allow us to obtain the positions of each of our galaxies. Then we have the corrector, we have the actual telescope where DESI is actually mounted on, which is the Mayal telescope. And then we have the spectrograph, which is going to read the radial direction for us. And then we have a picture on the bottom of the actual DESI instrument on the inside of the observatory. Now, as probably many of you know, DESI it's a survey which is running from 2021 all the way to 2026. And in these 5 years, DESI is going to obtain 40 million redshifts for our galaxies and for different 5 target classes. Specifically, we're going to have QSOs, emission line galaxies, luminous red galaxies, and then bright galaxies as well. And these measurements for redshift and for the three-dimensional distributions of our galaxies, the three-dimensional positions, it's going to run all the way from redshift 0 all the way to redshift 4. So again, it's going to be a very, very complete survey with a lot of incoming data. And so with this, let me just finish with the data. And so we're gonna we're gonna go into understanding the theory that we use in our group to try to prove for parity violation. So specifically, my group exploits endpoint correlation function, which you can think of them as excess probability over random of finding n galaxies in a specific R n-1 configuration. And so what I mean by this is, for example, take n equals to 2. Then what you have is the 2-point correlation function. What you're asking is what is the probability that I get a line of specific length r, and then asking, what is the probability that two galaxies are going to be sitting at the end of this specific size Rn in my survey. Then for the 3-point correlation function, n equals to 3, we are asking what is the excess probability over random of finding 3 galaxies in this specific triangular shape. For the 4 PCF, is the same thing, but asking what is the excess probability over random of finding 4 galaxies in a specific tetrahedral shape. Okay, and so if you are not as familiar maybe with endpoint correlation functions, then you might be asking why do we even bother in going to so many endpoint correlation functions. And again, these are different statistical properties that we're measuring with each of these endpoint correlation functions. So for example, with the 2 PCF, we are measuring Gaussian information, but then with the 3 and 4 PCF, we start to measure non-Gaussian information for the distribution of our galaxies. But then also, which is the most important for this conference, is going to be the fact that in a 3-dimensional setting, then the 4-point correlation function is actually the lowest order correlation function that is able to prove for parity violation. And so to do this, let's look at this picture that I have here where I'm going to try to explain how we test for cosmic parity violation using the 4-point correlation function. Again, so we are in a 3-dimensional survey, so just for example, DESI. And so we are forming our 4-point correlation functions. If you look at the tetrahedron that we have here on the left, then we are going to choose one galaxy as being the primary. So let's say that we're going to choose the primary galaxy as being the one on the top of the left tetrahedron. And so then we're going to draw 3 vectors to join, to complete our tetrahedron and then join the primary with the secondary galaxies. And so in this case, as it is shown on the top, then we have the red vector as being the shortest, the green as being the middle vector, and then the longest as being the blue. So if we choose this order and then we join the 3 vectors going from the shortest to the longest, then we can see that this gives us a hand for this specific tetrahedron. In this case, we have a clockwise rotation going around from shortest to longest, okay? Now, if we look at the mirror counterpart of this left-handed tetrahedron, then what we have is basically just the opposite. If we do the same thing where we're going from shortest to longest vector, then what we see is that we find a counterclockwise rotation of this tetrahedron. And so what this is indicating us is that because there's no way of rotating the tetrahedrons without maybe even reaching out into extra dimensions, there's no way for us in these 3 dimensions to just rotate the tetrahedrons and then make them equal to each other. So basically, this is a way of distinguishing between one parity and the other. Okay, so the 4 PCF is the lowest order correlation that allows us to test for this parity in the distributions of galaxies. So my work with the 4-point correlation function in reality has been more focused on using the even 4-point correlation function. But hopefully by the end of this talk, I'll show you how we are also helping the parity-odd case in trying to search for parity violation. So the first thing, just to mention what I've done, is we have theoretically modeled the even 4-point correlation function for galaxies. And so in this work, what we did was start from the Fourier space counterpart of the 4-point correlation function, which is known as the trispectrum. And so this trispectrum was composed of two terms, the ones that we call in T311 and T2211, which here I'm just trying to describe in terms of Feynman diagrams. But again, you don't have to really know what is going on. The only thing I wanted to mention is that we had this model, then we took its inverse Fourier transform to go back to configuration space and actually find that 4-point correlation function. Again, so it has a lot of very interesting math and a lot of nice properties that apply also to the parity violation theory structure. So if you want to check those out, I recommend you looking at this paper, which is a nice theory paper. Now, continuing into this theory world, one of the works that I've been working on is also on theoretically modeling the 4-point correlation covariance. The covariance give us information about our measure of the error of our measurements. So this is something that we really want to have as much pinned down as possible. And this is something that is very, very important for measuring the parity-odd 4-point correlation function. So if we don't have our covariance right, then we might have a wrong detection of parity violation. So just to give you a little bit of context of what I've been doing with modeling this 4-point correlation function covariance, is that back in 2021, sorry, Yamin Hu et al., they modeled the 4-point correlation function covariance, but only assuming a Gaussian random field. What I mean by this is that if we look at the 4-point correlation function in terms of pictures, then we are multiplying two 4-point correlation functions. So a primed 4-point correlation function and then a non-prime correlation function as we have here. And so at the vertex of each of these tetrahedrons, we have these black dots that they are representing a density contrast for the 4-point correlation function. Now, as you know, the density contrast gets expanded into a standard perturbation theory, okay? And so you can expand this density contrast. And in this work by Yamin et al., they only expanded up to first order. And so what you get is this 4-point correlation function covariance that it's only dependent on Gaussian contributions. So my work, what it did was expand on that work to also include non-Gaussian terms, or expand towards the second order and the third order density contrast. So again, here I'm only showing you the covariance expanded up to the second order density contrast, which we are trying to represent here on the top of each of the tetrahedrons, okay? So again, this work is going to be important in the sense that once we have really pinned down a good covariance, then we are going to be more confident on the measurements for parity violation. And so this, as of right now, was only a theoretical model that we have put out. We are also we are missing to do numerical analysis to really understand how much more information can we really gain from using a non-Gaussian covariance for the 4-point correlation function instead of just using the Gaussian covariance of the 4-point correlation function. And so this has been kind of like the extent of my theory work with the 4-point correlation function so far. So now going into the region where we are actually now starting to apply data plus math to try to extract that cosmological information. One of the most important things also to try to make sure that we have a true detection of parity violation with the 4-point correlation with the odd parity 4-point correlation function is to make sure that we get a good measurement of the even 4-point correlation function. And so before I continue, I will mention that the even 4-point correlation function, for example, in DESI, has been measured, for example, by Yamin Hu et al. Earlier this year, so like around August or September. And so we are actually also measuring the even 4-point correlation function in DESI using the same LRG sample. And while the analysis are similar, they are not going to be actually completely identical, because we are doing some different tests, and then we are also implementing different techniques into this analysis. Now, just to summarize what we are currently, what we are actually finishing up on doing for measuring the even 4-point correlation function, then what you see here is the North Galactic Cap and the South Galactic Cap for the DESI Year 1 luminous red galaxy sample. And so we are measuring the 4-point correlation function in the full North Galactic Cap and then also in the South Galactic Cap. But then, as you can see in these pictures, in these images, is that we are also have some regions that we have colored. Okay, so we have each these different colors for these regions that we are actually calling patches. And so within these patches, then what we're doing is actually also measuring the 4-point correlation function inside of each of those. We're doing that because this allows us to also test for consistencies and for systematic errors that we might have within our 4-point correlation function measurement. So again, I don't have much time to go into all the details, but I'm happy to talk more about that. So I want to show you now how the actual 4-point correlation function of DESI looks like. And so looking at any of these panels, then on the y-axis, what you're going to see is the actual coefficients from measuring the 4-point correlation function. Then on the x-axis, you're going to see the possible different tetahedrons that we form with the radial magnitudes of R1, R2, and R3. And then at the top of each panel, then what you're going to see is three different momentas, okay, L1, L2, and L3. And what they are representing is the three possible different angles that you are going to choose for your tetahedrons, okay? And so inside of each panel, then what you have is the actual 4-point correlation function measurement. For blue, for the dashed blue line, then you have DESI year 1. And then in the bands that are red and cyan color, then this represents the mocks that we have used to test for 4-point correlation function measurements. And as you can see, for example, on red, we have the easy mocks, and then on cyan, we have the abacus mocks. So let me continue now, because again, as I said, one of the most important things to do is actually also make sure that our 4-point correlation function measurements are agreeing with the data. As this was mentioned in a paper in 2024 by Alex Krolewski et al., it is important that the 4PCF agrees, the 4PCF measurement in the event sector agrees with the data, with the mocks. Otherwise, this could lead to discrepancies that also filtrate into the parity-odd 4-point correlation function measurement, and then it could create a parity violation signal that is not that is not real. And so having these tests where we are actually seeing that the mocks and the data are agreeing pretty much, then we can be more confident that the parity violation signals that we can see using the 4-point correlation function, or the parity-odd 4-point correlation function, are actually true. And so just to finish up, I quickly show you these results for the even 4-point correlation function, the actual detection significances that we find. On the left, what we're actually doing is measuring the 4-point correlation function using an empirical covariance, meaning that this has been done from the mocks. And then on the right is from using an analytical covariance. And I don't have much time left to try to explain how we're doing this analysis, but I'm happy to do that in the discussion. So please feel free to ask me. And thank you very much, and hope to see you soon.